view, admit all. Ayan, so ito yung ano, no, yung sa beam. Um, Madiderive nyo itong ano, itong stiffness matrix na to. So 4 by 4 din, no, kagaya ng sa axial, no, axial member. You can derive this using slope deflection. Okay, pakita ko. This is the the derivation of structural stiffness matrix of beam using slope deflection equation. You can derive this in many ways, like virtual work method, area moment method, finite element formulation. So for now, let's stick on slope deflection method. So this is the general equation for slope deflection method. As you remember, during TOS 2, oops, wala pa pala yung zoom in. Yan. So moment is equal to EI over L, 4 theta rotation on the other end plus 2 rotation theta on the other end plus 6 V1 over L. V1 means the vertical displacement minus 6 V2, the vertical displacement on the other end over L. And then, so if you write down the slope deflection equation to the from the for the other end, interchange nyo lang yung ano, theta, no? And even yung ano, yung V1 and V2. Zoom it. Admit all. Yan. So by equilibrium, remember how do we write down Fy? Yan, gumana na yung zoom in. Okay. Yan. So remember, if you have two moments, and, say, kaibang direction, how do you find the reaction? So by just equilibrium. No? So say this is M1, this is M2. So if you want to find F1 and F2, that is simply this equation. M1 plus M2 over L. So that's your F1. Okay. Then to find F2, uh, that is, of course, opposite to F1. That's why F2 is negative of M1 plus M2 over L. Okay? So you're doing this during ano, 'di ba? During moment distribution, during portal method, you know this formula already. Okay? So by substituting the formulas, yan. So M1 is MZ1 plus MZ2. You will come up with this. Okay? So as you notice, this becomes V1 becomes 12 because you're adding 6V1 and 6V1. Okay? And also V2 becomes negative 12. You're adding negative 6V2 and negative 6V2. Okay. And then 6 theta Z1 because you have 4 theta Z1 and 2 theta Z1. And 6 theta Z2, 2 theta Z2, 4 theta Z2. Okay. And and when you express that in matrix form, you have this. Okay. Because for example, Fy1, Fy1 is remember 12 12 V1 over L squared. So which is this 12 V1 over L squared, right? EI over L is here. Okay. Uh, in terms of V1, no? In terms of theta Z1, what is Fy1? You have 6 theta Z1 over L. So which is 6 theta Z1 over L. Okay. In terms of V2, negative 12 V2 over L squared. Negative 12 over L squared V2. Okay. And lastly, in terms of Z2, theta Z2, 6 theta Z2, 6 theta Z2 over L. Okay. And you can also derive this using area moment. Remember, for area moment, uh, this is fixed. Assume a unit deflection, 1 unit. No? And how many unknowns is this? Three. Three unknowns, diba? Because our equilibrium equation is 3. And we have indeterminacy 3. Okay, so you can um, solve this. No? Okay. But if you neglect axial, it will become two unknowns. No? So we're assuming in this stiffness matrix, the degrees of freedom of a beam is only 4. That's why it's 4 by 4. That means you have vertical deflection and rotation on both ends. Okay? That means this 12 over L squared corresponds to the reaction at this end. No? 12 over L squared, V1. 12, basically, that is 12 EI V1 over L cubed. Right? If you expand this one, 12 EI V1 over L cubed. That means that is the reaction, the vertical reaction on this end uh, if you have a 1 unit displacement, okay, on this end. So that's the idea, no? Then what is this? The moment here is 6 theta z1 over L squared over L squared. That's the moment. Siyempre, on the other ends, you will come up with the same numbers. Negative nga lang. Okay? That's why, no, I'll rewrite down the ano, no? So I said that if you have a 1 unit displacement, your reaction is 12 EI V1 over L cubed. That is the reaction F1 or FY1. No? I believe you're familiar with this. No? In our discussion on earthquake engineering, no? Remember the stiffness of a column is that formula. K is equal to 12 EI over H cube. H because nakatayo. No, it's standing, no? Which is very which is the same with our beam. Tinayo lang natin. That's why instead of using L, we use H. So in earthquake engineering, this is basically the stiffness of a a column. No? When you wanted to find the lateral stiffness of a building in a floor, no? Kung gusto niyo kunin yung lateral stiffness niyan, okay? Get the 12 EI over H cube of each column, then sum up that, so that will become the lateral stiffness of the story of the floor. Okay? That's why in STAAD, if you wanted to find soft story, STAAD will sum up all the stiffness in a floor compared with the other floor, and if there's a too much difference in stiffness, uh, it will come up with a sub-story failure. And you know that in most cases, in the last earthquakes that happened, soft story is the common failure. So that means, so my point is, that's how important this formula is. It is used in STAT. Okay, so that's it for the derivation. By the way, this is the this is the assumed deformation. Okay, so you have an arbitrary theta, arbitrary V1 and V2, okay, and we neglect the axial deformation. And if you notice, even if you model in STAAD, analyze your building, the beam will most of the time have no axial force, no? Because the beam is will behave, no, in bending talaga. Okay. That's why that means it's justified to assume there's no axial deformation. No axial deformation, therefore no axial force. And so by the way, uh, in this arbitrary deformation, you have the delta, no? And this delta is assumed as V2 minus V1, the difference between V2 and V1. That's why when we write down the slope deflection equation, this one, it becomes this. Okay? I'd like also to discuss the what happens to your matrix, no, when you have instability. No? So it's very interesting because ay, pati stability na type ko. Stat. Because all softwares, no, as I said, no, all softwares are using this method, the stiffness analysis, stiff matrix analysis, in analyzing the structure. No? So there will be a lot of times now, when, especially when you're a beginner, there will be instability warnings. So why does instability happens? No? How do you prevent it? No? And what happens to your matrix, no, during instability warning? I have uh, an example here. Yung trust natin before. Where is that? Nawawala. This one. Yeah. So to give you an idea, Okay, so remember this structure. No, we have an actual member. No? So what I did is let's remove the supports, and then subject that to a force. So for sure, uh, you know what will happen. No? It will no, it will have a large displacement, right? Because you only rely on one support. Okay, and your matrix, your S matrix will become what size? So remember, you have DOF, 2 degrees of freedom per node. And your S matrix depends on the number of unknowns. So how many unknowns do we have here? 1, 2, 3, 4, 5, 6. That means your S will be 6 by 6 because you don't have supports here. Okay? So if I apply the force here, we will get 6 unknowns, no? 6 displacements, which is this is the size, no? Or our S. And if we apply this coding 1, 2, 5, 6, 7, 8, so this is our S with the corresponding code 1, 2, 5, 6, 7, 8. And if you do that manually or in Excel, oops, what happened? This is will be your matrix, S matrix. So 1, 2, 5, 6, 7, 8. And this is the matrix, the inverse of the matrix. And if you find the determinant, no, find the determinant of this matrix, no, it has determinant because it's a square matrix. You will come up with almost zero determinant. Point 2.52 times 10 raised to 9, negative 9. So zero determinant, and that means your matrix is a singular matrix. Yan, no? Singular matrix. So what is a singular matrix? Is the one in which non-invertible. There is no multiplicative inverse B such that a matrix is singular if and only if its determinant is zero. Yan. Okay? And when you model that in STAAD, this will happen. Warning, instability at joint 2. STAAD detects instabilities as excessive loss of significant digits. Instability, very weak spring. Okay? So you see that is the physical meaning, no? That is the physical meaning of your S matrix. Huh? So very uh, that's very interesting, no? Actually, when I first learned that, uh, it will give you a lot of insights, no, na okay, that's how the software works, no. Whenever you have an instability, that means internally your S matrix has problem. Okay? Ayan. So this is our example problem before. So I'll view this. Oh, it's different. Anyway, I can I can come up with another. Should it? Wait lang. And so I'll remove the supports, no? Okay, so combo number 2, select this command and then select these two. Yan. And then assign, then run. So we have two warnings. Let's view the output file to see the warnings. And so same result, right? We stat detects instability. No? Okay. So excessive loss of significant digits. You can now realize, no, because as you see here, no, yung ating matrix, no, we have lots of digits there, no. So almost zeros, no, on the other on the other cells, no. And yeah, it's still the same because it's still a three member. So yeah, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So our S matrix here is also 6 by 6. So you might you might come up with almost the same um, matrix, no? 6 by 6 also. Di ko lang makita yung yung itong file na to. Okay. So that's a singular matrix. And if you want to see the deformation, post processing, and then okay, displacements, yan, di ba? Hindi na makita. And unrealistic na yung mga mga displacement. See? Okay. So it's a proof that you have an unstable structure. Okay, so that's it for the singularity, singular matrix. So that's the physical meaning. And we can now proceed sa beam.